let's talk about doing proofs in trigonometry. And specifically, let's talk about some strategies that you can use to do proofs. In the last video, I showed you the structure that I like my students to use when writing trigonometric proofs, proving trigonometric identities. In this video, I want to talk a little bit about different types of trigonometric expressions. While there's no hard and fast rule, the form that a trigonometric expression is in may suggest a particular strategy. A big part of figuring out which strategy to use is making observations about the form the expressions are in. On the right-hand side of this identity, there are two fractions. One has the denominator 1 minus the sine of x. The other one has the denominator 1 plus the sine of x. If we were to add these two fractions together, we'd need a common denominator. That common denominator is going to contain the factors of 1 minus sine x and 1 plus sine x, which, when you multiply them together, gives you 1 minus the sine squared of x, which is a difference of squares. Here's another problem. Verify the identity. In this case, the left-hand side of the identity is a fraction, and it contains 1 minus the sine of u. This problem looks very different from the other one, but I notice that since I have a 1 minus the sine of u, I could choose to multiply the top and bottom of this fraction by 1 plus the sine of u, thereby introducing the difference of squares. Why is the difference of squares so important? Well, remember that 1 minus the sine squared of x is an identity for the cosine squared of x. So if I can find a way to write an expression as 1 minus sine squared of x, or 1 minus sine squared of u, then I can substitute cosine squared of x, or cosine squared of u. Let's go ahead and see this one through. As I said, it's the right-hand side that I want to change by introducing a difference of squares. So I'm going to start my proof by saying the right-hand side is equal to 1 over 1 minus the sine of x minus 1 over 1 plus the sine of x. Again, I have not done anything to the right-hand side yet. I've simply rewritten it. In my next step, I'm going to introduce a factor in both cases that will allow me to write this as a difference of squares. So here's my 1 over 1 minus the sine of x, and I'm going to leave room to multiply, and then minus 1 over 1 plus the sine of x, and I'll leave room to multiply there. My common denominator contains both of the factors 1 minus the sine of x and 1 plus the sine of x. So I'm going to multiply the first fraction by 1 plus the sine of x over itself. The second fraction also needs to contain both factors 1 plus the sine of x and 1 minus the sine of x. So to introduce that factor in the denominator, I must also introduce it in the numerator. Now, when I multiply the numerators together, for the first fraction I get 1 times 1 plus the sine of x, and that's going to be over now the product of 1 minus the sine of x and 1 plus the sine of x, which is 1 minus sine squared of x. In my second pair of fractions, when I multiply 1 by 1 minus the sine of x, I get just 1 minus the sine of x. But it too is over the common denominator of 1 minus sine squared of x. Now, because I have a common denominator, I can combine these two numerators. I have 1 plus the sine of x minus, notice here I need to distribute my minus. So I have minus 1 minus negative or plus the sine of x, and that's all over 1 minus sine squared of x. Now combining my terms in the numerator, 1 and -1, cancel, and I'm left with 2 copies of the sine of x over 1 minus sine squared of x. I'm going to rewrite my numerator, 2 times the sine of x, and I'm going to substitute cosine squared for 1 minus sine squared. That's just one of our identities. It comes from sine squared of x plus cosine squared of x equals 1. But in this case, I've subtracted the sine of x from sine squared of x from both sides. So I can write sine squared plus cosine squared equals 1, or I can write cosine squared equals 1 minus the sine of x, sine squared of x. So that's all I've done here. Now I'm going to choose to write this quotient in a very particular way. I'm going to leave my 2 out front, and I'm going to say that sine over 1 copy of cosine and multiply that by 1 over the remaining copy of cosine. So I have 2 times sine divided by cosine squared. I've just written it a different way. And I've done that because I specifically want to be able to write my final answer as 2 times tangent, which sine over cosine is, tangent of x, times 1 over cosine, which is secant of x. Now that's it, but what I've had to do is show that this right-hand side, the side I started with, is equal to the left-hand side. So ultimately, I also need to include equals left-hand side. And now I'm finished. As you can see, changing the right-hand side so that the denominator was cosine squared was very important. In order to do that, we recognized that difference, 1 minus sine, as something we could use, we could build on, to get 1 minus sine squared, a difference of squares. Once we had 1 minus sine squared, we could replace it with cosine squared. Let's try the other one. Here's our instructions. Verify the identity. The cosine of u over 1 minus the sine of u is equal to the secant of u plus the tangent of u. I'm going to use the same strategy here, but this time I need to recognize that in order to get a difference of squares, 1 minus sine squared, I'm going to have to introduce a 1 plus sine squared somehow. Let's just go ahead and do that. Before I begin, though, I need to pick a side, and since I'm going to be playing with this side, turning the denominator into a difference of squares, I'm going to start with left-hand side equals, and then just copy out the left-hand side, not changing anything at this point. What I'm saying here is that the left-hand side is given, and it is equal to the quotient, the cosine of u, over 1 minus the sine of u. That, in turn, is equal to something else. And that is going to be the first place where I'm allowed to actually change the form that this quotient is in. I'll start by rewriting the quotient, and now I'm going to multiply it by 1. But I'm going to multiply it by 1 in this particular form because I want the difference of squares, 1 minus the sine squared, in the denominator. It's very tempting to distribute here. Cosine of u times 1 plus cosine of u times sine of u. It's not wrong if you do. But I'm going to avoid that because I know that if I'm lucky, my denominator will factor, and I'll be able to cancel one of the factors, cosine of u or 1 plus the sine of u, with one of the factors in the denominator. So I'm going to leave it in its factored form for the moment. The numerator, therefore, is cosine of u times 1 plus the sine of u. That's all over 1 minus the sine squared of u. Again, it doesn't necessarily seem obvious at this point, but finding that difference of squares has been critical, because now I can say that this is equal to the cosine of u times 1 plus the sine of u over an identity for 1 minus sine squared, which is cosine squared. Now that I've done that, I'll make another observation, which is that because I have a factor of cosine of u in the numerator and 2 factors of it in the denominator, I can cancel one of those and leave the other. My first statement, that the left-hand side is equal to cosine over 1 minus sine, is equal to cosine minus 1 minus sine when you multiply it by 1. That is in turn equal to cosine times 1 plus sine over 1 minus sine squared because of some algebra that I did. And that step is equal to the next one, and that step is equal to the next one, and so on. The next one in this case is what's left once I've canceled one copy of the cosine in the numerator and the denominator. And that's 1 plus the sine of u over the cosine of u. That expression is in turn equal to this expression, and this is just another algebraic trick. I can write this as 1 over the cosine of u plus the sine of u over the cosine of u, splitting my fraction up into 2. It's like I'm unadding together 2 fractions that have a common denominator. But now I can see that 1 over cosine of u has its own identity of secant, so I'll replace that one. And sine of u over cosine of u is tangent of u. I started with my left-hand side, cosine of u over 1 minus the sine of u, and I've stated in a series of equalities that that first statement was equal to the second, and so on, until it was equal to the secant of u plus the tangent of u. But the secant of u plus the tangent of u is exactly what I have on the right-hand side of my identity. So I'm done. I've proved this identity by showing that the left-hand side, which I had here, was equal to the right-hand side. But I had to get there by going through the algebraic steps and the trigonometric substitutions. So that's one strategy. Find a common denominator, especially where that common denominator is a difference of squares. It won't work for everything, but if you see a difference or a sum in a denominator somewhere in your identity, it may be a strategy that will work for that particular problem. Let's try this one. Another common strategy is to turn everything into sines and cosines. Some people think of that as a sort of last-ditch effort strategy, but it's not a bad one to try right off the bat either. Sines and cosines are more familiar, more comfortable, and it's easier to work with them in a lot of cases. Tangents and cotangents are easy to turn into sines and cosines. So let's start with that with this one. Notice that the numerator of the fraction on the left-hand side has a tangent of x plus a tangent of y. X and y are the angles here. They're different, and that's important. But we can turn the tangent of x into the sine of x over the cosine of x, and the tangent of y into the sine of y over the cosine of y, and so on. We are being asked to verify this identity, so as with all of our other problems so far, we're going to start with either the left-hand side or the right-hand side. Because it's more complex looking, I'm going to start with the left-hand side. That gives me more to play with. The left-hand side is tangent of x plus tangent of y over cotangent of x plus cotangent of y. And I'm just copying it out, not making any changes. What I'm saying is the left-hand side is given, and it is given as being equal to this ratio. That ratio, though, is in turn equal to something else, and that something else is going to be just tangent of x plus tangent of y over cotangent of x plus cotangent of y, written a different way. Tangent of x can be written as sine of x over cosine of x. Tangent of y can be written as sine of y over cosine of y. Cotangent of x can be written as cosine of x over sine of x. And cotangent of y can be written as cosine of y over sine of y. Now what we have is a complex fraction. So in spite of the fact that I said this was a different strategy, we did start a different way, but we're still going to need to find a common denominator, combine the two ratios in our numerator and the two ratios in our denominator, and then see if we can find a way to simplify the resulting rational expression. The common denominator in the numerator needs to have a cosine of y and a cosine of x in it. So I'm going to multiply the top and the bottom of this fraction by cosine of x, and the top and bottom of this fraction by cosine of y. I'll do the same thing in the denominator. Here, the common denominator needs to be sine of x times sine of y. So I'm going to introduce sine of y in this ratio and sine of x in this ratio. And now I'll simplify. In the numerator, I have sine x cosine y plus sine of y cosine of x, all over the common denominator of cosine x cosine y. That's the numerator of my overall ratio. The denominator has sine of y cosine of x plus sine of x cosine of y. And that's all over the common denominator of sine of x sine of y. And by doing this algebraic manipulation and trigonometric substitution, what I'm saying is that the step above this is equal to this new version of the problem. Let's finish up here. This new line is equal to another one that I'll write. This time I'm going to rewrite the problem not as the ratio of two fractions, but as the product of two fractions. In other words, algebraically, I'm going to multiply by the reciprocal instead of dividing by the fraction. So I have the sine of x times the cosine of y plus the sine of y times the cosine of x over cosine x cosine y. And I'm going to multiply that by the reciprocal of the denominator. So I have sine of x sine of y over sine y cosine x plus sine x cosine y. Now they're in a different order, but notice that sine x cosine y plus sine y cosine x appears both here and here. Since addition is commutative, these are the same and I can cancel them. And that leaves me with sine of x sine of y over cosine of x cosine of y. Maybe you can see it now, but just in case you can't, remember that you can multiply two fractions together to create a single fraction. In the same way, you can unmultiply two fractions. So I'm going to rewrite this as the sine of x over the cosine of x times the sine of y over the cosine of y. And now I'm going to use the identity tangent equals sine over cosine backwards. This gives me tangent of x times tangent of y. And that's what I was asked to prove, that the left-hand side, the thing I started with, was equal to tan x tan y. That's what I've got now. So I can say that this last line is equal to the right-hand side. Here's another identity we've been asked to verify. Secant to the fourth of x minus tangent to the fourth of x is equal to secant squared of x plus tangent squared of x. The strategy at play here is observe some algebra. Although this is a trigonometric problem and it's tempting just to start writing in substitutions, notice that the left-hand side of this identity is a difference of squares where the things being squared are secant squared and tangent squared. In other words, I could write this as secant squared of x squared minus tangent squared of x squared. And the difference of squares here gives me secant squared of x plus tangent squared of x times secant squared of x minus tangent squared of x. So it's important not to forget your algebra. This is actually the trick we're going to use to get this one done. But I'm going about it a little bit ahead of myself. First of all, I need to establish which side I'm going to start with and then work my way through it algebraically. So let's back up. And having made that observation, I am going to go ahead and start with the left-hand side, because this left-hand side is given, secant to the fourth of x minus tangent to the fourth of x, and I now know that one of the things that I can do, or the thing that I'm going to try in this case anyway, is to rewrite this algebraically, factoring this difference of squares into the secant squared of x minus the tangent squared of x times the secant squared of x plus the tangent squared of x. How does that help? Well, if you remember that sine squared of x plus cosine squared of x equals 1, and you divide both sides of this equation by cosine squared of x, then you get sine squared of x over cosine squared of x plus cosine squared of x over cosine squared of x equals 1 over cosine squared of x. And this simplifies to tangent squared of x plus 1 equals secant squared of x. Well, that's very similar to what I have here, but it's not quite in the right form yet. If I want secant squared of x minus tangent squared of x, then I need to subtract tangent squared of x from both sides, which gives me 1 equals the secant squared of x minus tangent squared of x. That means that I can substitute a 1 in anywhere that I see secant squared of x minus tangent squared of x. And that means this is really just 1 times secant squared of x plus tangent squared of x, which is, of course, secant squared of x plus tangent squared of x. And that's actually what I was looking for. So that's equals right-hand side. Now, this one actually took very little time to do, but I had to make the observation that by factoring this difference of squares, I would end up with something that had this difference of two squares in it. And that difference of two squares is not the same as the 1 minus sine squared or 1 minus cosine squared that we've dealt with so far. You won't be expected to reinvent this wheel every time you need a difference of squares containing some trigonometric expressions. But it's important that you recognize that either a difference of two squares or sometimes a sum of two squares, although not in this case, in trigonometry is often something you can substitute. So although this problem didn't take very long, the strategy here is recognizing formulas. Most of the time when you work on these, you'll be at home or sitting at the library. You don't necessarily need to have memorized all of these formulas. Of course, that depends on your instructor. My point here is that you should be familiar with as many of the identities as possible so that you can recognize them when they come into play. This one's really not obvious. A lot of people, especially when they're just learning how to do these for the first time, when trigonometry is still a relatively new skill, won't recognize this secant squared x minus tangent squared x as something obvious that can be substituted for. So let's recap some of the strategies we've talked about so far. I never explicitly said to do any of the obvious algebra like expanding a product of binomials or factoring. But it's certainly something to keep in mind. Remember that all we're doing with these is changing the form that they're in, and we're trying to do that in a very particular way. But until you know whether one strategy you try is going to work or not, it's worth trying a couple and just factoring or expanding or finding a common denominator is one thing that you can do. Another strategy is to convert everything to either a sine or a cosine or a combination of those, like turning tangent into sine over cosine. It doesn't work for everything, so this strategy might not work for every problem that you do. And remember that if you convert everything into sine and cosine, you might need to be able to convert it back out of sine and cosine at the end, if your right-hand side is tangent or secant squared, for example. This one really comes more with practice, but know your identities. Have a formula sheet handy so that you can refer to it whenever you're working on one of these problems. If you can't see an obvious substitution, look to see if there are things that you could modify slightly to make them into something that could be substituted. That's where the difference of squares trick comes in. One way to do that is to add two fractions together, especially if they are already factors that, when multiplied, would produce a difference of squares, like 1 plus sign in one denominator and 1 minus sign in another. If you only have one fraction, then multiply it by 1, but multiply it by the conjugate of the denominator, which will create a difference of squares. Honestly, I know nobody wants to hear this one, but seriously, just like playing basketball, the more practice you get in, the better you're going to get at it. The more you work through problems that require your brain to bend in a particular way, the better your brain is going to get at bending that way. You'll learn to recognize identities because you see them so often. The more you practice, the better you'll get at looking at a problem and saying, this one looks like a difference of squares type of problem, or this one looks almost like one of my Pythagorean identities. In the next video, I'm going to walk through doing one of these proofs that I haven't prepared in advance, so I won't necessarily know exactly which step is going to come next. I'm going to do that on purpose because I want you to see what it looks like when you're working through one of these from scratch.